Hello, welcome to the fourth lecture in this lecture series of angular momentum algebra. In this video, I'm going to talk about the spin angular momentum algebra of the electron and how these different components of a spin angular momentum are related to the different Pauli matrices. In case you have not watched my earlier videos, I have provided the link in the description box. So let's get started. Before I discuss the spin angular momentum algebra, let me provide a quick recap what we have already learned in the previous three videos. So we have taken the general angular momentum of an electron specifically. So J represents the total angular momentum or the generalized angular momentum, which could be in general L plus S, where L is the orbital angular momentum of electron and S the spin angular momentum of the electron. We have already discussed and derived these computation relations Jx, Jy, Jy, Jz and Jz, Zx and J square with these components of generalized angular momentum Jx, Jy, Z. All these relations we have already derived. The J square commutes with all three components and they are Jx, Jy is IH cross Jz, Jy, Jz is IH cross Jx and other thing. Similarly, we have defined the common eigenstates of J square and Jz to be J comma M, where J comma M are two quantum numbers where M can vary from minus J to plus J in the unit step, that is minus J plus 1 and so on and so forth up to plus J. That is, there are total 2J plus 1 values for M for a fixed value of J, small j. Now action of J square on this eigenstate we have already taken like this and Jz on J comma M is MH cross J comma M. So we defined for the raising and lowering operator. Raising operator is Jx plus iota Jy, lowering operator is Jx minus iota Jy. With the help of these raising and lowering operator, we can write down the expression for Jx and Jy in terms of these J plus and J minus. The action of J plus on this state gives us this value and it raises the value of M by 1, and action of J minus on this state is lowers down the M value by 1 and it gives us this result. The same algebra is followed by the spin angular momentum of the electron also. Simply you have to replace J by S. Everything else is same. So we can find out the computation relation among different components of a spin angular momentum S like this, and S square, which will be S square is nothing but Sx square plus Sy square plus Sz square. As in this case it was J square was Jx square plus Jy square plus Jz square, and the common eigenstates of S square and Az, because they both commute, so they will have a common eigenstates, set of common eigenstates which you have taken to be small s comma M sub small s, where this small s and M sub small s, they are quantum numbers where Ms can vary in the same pattern, minus small s to plus small s in the unit steps, that is minus s plus 1 and so on and so forth up to plus s. In case of electron, small s is half. So for a spin half particle, small s is half, that is Ms value, allowed values of Ms are minus half and plus half, right? So allowed values of Ms are minus half and plus half. The action of S square on S comma Ms would be S into S plus 1 H cross square S comma Ms, and similarly Sz on this state will give us Ms H cross and the state back. Raising and lowering operator can be defined on the same pattern, S plus equal to Sx plus iota Jy, Sy equal to Xx minus Ij minus Sy, and similarly we can find out X and Sy in terms of S plus and S minus, and the action of S plus and X minus on S comma S will be given by in the same footing as we have discussed in case of capital J, and it will S plus will raise the small value of a small s Ms by 1 and it will lower down the value of a small ms by 1. So in the previous video we wrote down the matrix representation for generalized angular momentum J for a fixed value of small j. In the previous video we took small j to be 1 and then we found out the matrix representation of each and every operator involved in this algebra. Similarly, in this present video what we are going to do is, first of all, that we for a fixed value of a small s, for example for spin half particles like electron, small s is half, so we are going to find out the matrix representation of every operator involved in the theory, that is Sx, Sy, Sz, all the three components, S square, Sz, S plus and S minus, all these. So let's get started. Okay, so let's have a look on matrix representation of operator S square. For small s equal to half, and ms equal to allowed values of ms would be corresponding minus half and plus half. So the action of s square on s comma ms state is this, and the possible states are half comma half and half comma minus half, half comma half and half comma minus half, corresponding to two different values of ms. So we have already done this kind of similar kind of discussion for J in the previous video, so it will be easy to follow if you have already seen that video. So from this equation itself here, we can see that the matrix of S square will be a diagonal one because the off diagonal term would be 0. So half half with half half will give me half into 3 by 2 h cross square, because s is small s is half, and this will give me 0. This will give me 0, and this will give me again 3 by half into 3 by 2 h cross square. Okay, so ultimately what we get is 3 by 4 h cross square 1001. 3 by 4 h cross square times identity matrix. So similarly, we can look for the matrix representation of SZ operator. SZ operator follows this eigenvalue equation. S comma ms is equal to ms h cross s comma ms. So again, this will have a diagonal matrix. So the states are half, half, and half minus half, and here half, half, and half minus half. So this will be off diagonal term would be 0, and the diagonal term would be h cross by 2 here, because ms is plus half here. In this case, it will be minus half h cross because of this ms value being minus half h cross. So what we get is h cross by 2, 100 minus 1 as the matrix representation for SZ. Now have a look on the matrix representation of other operators like s plus, s minus, and then sx, xy. So matrix representation of s plus operator. Matrix representation for s plus again can be deduced by if the action of s plus on s comma s, which is h cross under the root s into s plus 1 minus ms into ms plus 1 s comma ms plus 1. So from this particular equation, we see that the matrix representation for S plus will be such that the diagonal elements are going to be 0. Because for diagonal elements, this time, if I take, for example, what are the possible states for S small s equal to half? These are half, half, and half minus half. Similarly, it will be half, half. So for S plus, for matrix representation of S plus, we get these states half, half, half minus half, half minus half as earlier. And from this equation itself, we see that the matrix is going to be going to have the diagonal terms to be 0. Because if both the states in the left and the right of this, suppose I multiply by the bra s ms from the left, so this when bra s ms will get an inner product with this get s ms plus 1, this will be 0 because these states we have taken to be orthonormal states. In other words, these states s ms is s prime ms prime, for example. So this is equal delta ss prime delta ms prime. On the same footing as we discussed in the last video about the j comma m states of generalized angular momentum. So since these states are orthonormal states, so I am going to get the following result. So for this case it will be 0, for this case it will be 0, however for this case it will give a non-zero value and we will put s small s equal to half and ms equal to minus half here. So what we get is h cross under the root half into 3 by 2 minus ms is minus half, so I give plus half into plus half. And for this case, when s plus acts on this, half comma half, so it will raise ms by 1, that is ms 3 by 2, which is not allowed, so this is going to be 0. Okay, so that's how we get, and we get the ultimate matrix representation for s plus s under root 3 by 4 plus 1 by 4, that is 1, that is h cross 0 1 0 1 0 0, sorry, 0 1 0 0. So that is the matrix representation for s plus. Similarly, we can do for s minus. The only thing we have to keep in our mind, two things we have to keep in our mind while writing down these matrix representation for these operators, that what are these equations. If there is you have eigenvalue equation, like in case of s square and sz, then eigenvalue equation, or otherwise what is the action of these operator on this state s comma ms. And one another important thing that we have to keep in our mind is that these states are orthonormal states, that is, they follow this relation, they are orthonormal states. So if we keep all these two things in our mind, we will be able to write down the matrix representation. So matrix for s minus in case of s equal to half would be, the action of s minus on s ms would be on h cross under the root s into s plus 1 minus ms into ms minus 1 s ms minus 1. So the matrix would become, these are the states, half half, half minus half, and half half, and half minus half. So this will be 0 element, because when s minus x on it, it reduces ms by 1, that is, makes a state of half minus half type, which will give 0 with this. Similarly, when s minus act on this, it gives a state half of minus 3 by 2 type, which is not allowed here in this case for s equal to half. And for this case, however, it gives a non-zero value, because when s minus act on this, it gives a state of half of minus half type, which give a non-zero value, and the value will be h cross under the root half into 3 by 2 minus ms is half here, so half into minus half. And in this case, it will again give me 0, because when s minus x on this, minus 3 by 2 is not allowed. So what we ultimately get is h cross equal to 0 0 under root 3 by 4 plus 1 by 4 makes this 1 0. So that is the matrix representation for s minus. So matrix representation for sx can be written as, the action of sx on s comma ms can be found out with the help of the expression of sx in terms of s plus and s minus, which is s plus plus s minus on s comma ms, which will give us half of h cross under the root s into n plus 1 minus ms into ms plus 1 s ms plus 1 plus h cross by 2 under root s into s plus 1 minus ms into ms minus 1. This is ms minus 1 s ms minus 1. Okay, this is half this, that's it. So if we find out, for example, the matrix representation Sx, this would be, if states are same, half half and half of minus half, and similarly here, half half and half of minus half, the matrix becomes, for this case, as an s plus x on this, it raises small s by 1, which is not allowed. So this portion is 0, because that will give a state of half comma 3 by 2 types. And when this s minus act on this, s minus act on this, so this gives me half minus half kind of a state, which will further give me 0 with this. So this is 0. When s plus acts on this, this gives half comma kind of a state. So the first portion is given will give a non-zero value, while when s minus act on this, it gives state of half comma minus 3 by 2 type, which will give 0. So the second portion will be 0. The first portion will give us non-zero value, and that will be equal to half h cross under the root S is half into 3 by, S is half, so half into 3 by 2 minus, MS is minus half here, so plus half into half. So that's the value that we get. Similarly here, if we see the S plus acts on this, so this will give 0 because half comma 3 by 2 states not allowed. The first portion is 0. When S minus act on this, however, this gives half comma minus half kind of a state. We will give non-zero value with this, and the value would be h cross by 2 under the root. S is half, so half into 3 by 2. MS is half here, so MS is half, half into minus half, that will be the value. And for this S plus act on this, give half comma half state, which will give 0 with this. When S minus act on this, again will give 0. So the matrix representation for Sx becomes, so these two values are same under the root, and h cross by 2 is also same, so I can take out, and this value is under root 3 by 4 plus 1 by 4, that is 1, under root 3 by 4 plus 1 by 4, that is 1, so 0 1 1 0. So this is my Sx. Similarly, if we find out Sy, matrix representation for Sy, so Sy, matrix for Sy, matrix for representation for Sy, so that can be found out with the help of this relation. So S comma ms, this is half of S, half 1 over 2 iota rather, S plus minus S minus acting on S comma ms. So this gives us 1 over 2 iota h cross under the root S into S plus 1 minus ms into ms plus 1 S comma ms plus 1 minus h cross under the root S into S plus 1 minus ms into ms minus 1 S comma ms minus 1. So that's what we get. And if we construct the matrix for Sy, so this is half comma half type, and this half comma half state, this is half comma minus half state, and this is half comma half is bra, and this is half comma minus half cat. So we'll see when S plus act on this, so this gives me half comma 3 by 2 state, which is not allowed. The first portion gives 0. When S plus act on this, when S minus act on this, however, so this is half of minus half kind of a state, will give 0 with this. Similarly, when S plus act on this, it gives half comma half kind of a state, which will give non-zero value with this. However, when S minus act on this, it will give 0. So the first portion gives non-zero value, and the value is 1 over 2 iota h cross under the root S is half, so half into 3 by 2 minus ms is minus half, the plus half into minus half, plus half into plus half, because ms is minus half, the minus half plus 1 is plus half. What do we see here? When S plus act on this, again this will give 0. When S minus act on this will give non-zero value, and the value would be minus h cross by 2 iota, and under the root S is half, so half into 3 by 2, and ms is minus half, and ms is plus half in this case, because S minus is acting on this, so ms is plus half, so minus half into half minus 1, which is minus half again. So that's it. Alright, so and for this particular case, again we are going to get 0 value, because both S plus and S minus will raise or lower down the value of ms, which will give 0 with this. So what we get ultimately is h cross upon 2 iota, and under the root 3 by 4 plus 1 by 4, same story here, so that's it, and 0 1 minus 1 0. Okay, if wish, we can write down this thing as s cross by 2 0 minus iota iota 0. Alright, so I can take 1 over iota inside, and that will give us this result. So we have found out ultimately the matrix representation for all the operators for s square, sz, s plus, s minus, sx, sy. Alright, where sx is given by this representation, sy is given by this, and if we remember, we found out s cross by 2 1 0 0 minus 1. Alright, so So let me write down what we have got so far. So we have got Sx equal to h cross by 2 for particles like electron, for spin half particles, h cross by 2, 0 1 1 0. Sy was h cross by 2 0 minus iota iota 0, and Sz was h cross by 2 1 0 0 minus 1. So that's what we have obtained so far. So where these matrices in the product of h cross by 2 have a specific names. So this is known as h cross by 2 sigma x, this is h cross by 2 sigma y, and this is h cross by 2 sigma z. Where this sigma x, sigma y and sigma z, they are called Pauli matrices. Pauli matrices. Pauli matrices. There are three components of Pauli matrix: sigma x, sigma y, and sigma z. These Pauli matrices have very interesting properties. Number one property is the properties of Pauli matrices. Number one, if we look at the trace of this, trace of sigma s, trace of sigma y, trace of sigma z, for example. Trace means if we add up the diagonal elements of sigma x, that is 0. If we add up the diagonal elements of sigma y, that is also 0. And if we add up the elements of sigma z, that is also 0. So this is the trace for all this sigma x, sigma y, sigma z is 0. Number 2, so determinant of sigma x, sigma y, and sigma z, if we find out, that is minus 1. 0, 0 and minus 1. Similarly for this. Third property that can be seen, that sigma x, sigma y, and sigma z, they are Hermitian. Right? They are Hermitian. That means if we take a complex conjugate and then transpose of this matrix, that is same. We can see a complex conjugate will not affect because it has real entry, and transpose will give me the same. 0, 1 will convert, row will be converted into columns, and we'll get the same matrix. Similarly, here, we take a complex conjugate and then transpose, we get the same matrix back. Similarly, here we take a complex conjugate and then transpose, we get the same matrix back. Here. So these are Hermitian in nature. Since they are Hermitian, they will have a real eigenvalues, and the eigenvalues of sigma x, sigma y, and sigma z are plus minus 1. If you calculate, for example, if you subtract lambda from both the diagonal elements, so lambda square minus 1 will equal to 1, so lambda square will equal to plus 1, which is lambda is plus minus 1, that their eigenvalues are plus minus 1. Similarly, we can check out for this and this also. Okay, so that's the fourth property. Another property, interesting property, is that if we take the commutator of sigma x, sigma y, that will turn out to be 2 iota times sigma z. Let's check out. The commutator on the left hand side is equal to sigma x, sigma y minus sigma y, sigma x, which is equal to sigma x is 0, 1, 1, 0. Sigma y is 0 minus iota iota 0, sigma y is 0 minus iota iota 0, sigma x is 0, 1, 1, 0. So that's what we get. We get 0, this is iota, 0 and 1 into iota is iota, this is 0, this is again 0, this is minus iota, this is minus iota, this is 0, and this one is 0 again, and this one is iota. So with the minus sign, if we take inside, so this will become twice of iota 0, 0, iota, minus iota. Right? Because minus sign will go to make it plus iota, it will minus iota, which is exactly same. So which is equal to 2 times iota 1, 0, 0 minus 1, which is nothing but sigma z. So 2 iota sigma z. Similarly, we can write down for others. If we check out sigma y, sigma z, commutator will be twice of iota sigma x, and sigma z, sigma x would be twice of sigma y. Okay. The sixth interesting property is that if we take the anti-commutator of sigma x, sigma y, then it will come out to be 0. Let's check out sigma x, sigma y plus sigma y, sigma x. We have just found out these two products. These were this. Instead of minus, if you have plus, so you will have the iota 0, 0 minus iota plus minus iota 0, 0 iota, which is nothing but 0. 0 means the null matrix. 0 means this is the null matrix. 0, 0, 0, 0. Okay. And similarly, if we see that sigma y, sigma z they will also anti-commute, and sigma z, sigma x will also anti-commute. All right. Seventh point. So if A and B are two vectors of, let's say, a linear vector space, which is Hilbert space, for example, in our case in quantum mechanics. So if there are two vectors of that, and if different components of these vectors, that is ax, ay, az, bx, by, bz, commute with sigma x, sigma y, and sigma z. So it can be shown that the sigma dot A, sigma dot B is equal to A dot B plus iota sigma dot A cross B. So if you wish, we can put a vector sign to notate, to denote that these are vectors here. I can write this expression as this if I wish. Okay, so that's the same. So this is the property that can be proved very easily. If we take the, for example, dot product here and dot product here, and then use this property that they compute the different components with this sigma, sigma y, sigma z. So left hand side can be very easily written in terms of the right hand side. Another interesting or simple property rather, that when sigma x and sigma y is actually equal to I sigma z, because if you say sigma x, sigma y that we calculated was equal to iota 0, 0 minus iota, which if we take iota outside, so we had already seen that sigma x, sigma y was iota 0, 0 minus iota. So if I take iota, so this will be 1, 0, 0 minus 1, which is nothing but sigma z, is iota of sigma z. Similarly, if we check out sigma y, sigma z, this is nothing but iota of sigma x, and sigma z, sigma x is nothing but iota of sigma y. Okay, so this is the eighth property that you can discuss. Another property can be written down. Take the sigma x square, for example. Let's check out what we get. So sigma x square, if we take, so sigma x is 0, 1, 1, 0. So if we take 0, 1, 1, 0, so this will give me 0, 1, 1 and 0, 0, 0 and 1, 0, 0 and 1, 1, 1. So this is nothing but identity of 2 cross 2. Similarly, if we find out sigma y square and sigma z square, these are also identity. So these are the few important and interesting properties of Pauli matrices. So what we have learned in this video is that we learned how to write down the matrix representation of different operators involved in the spin angular momentum algebra theory, x square, sz, sx, sy, sz, for a given value of small s equal to half, which is half for spin half particles. And we also defined Pauli matrices, and we also discussed their interesting properties. Thank you. Thanks for watching.